Hi, my name is Carly Lossie, and this is my Lab 5 presentation, Choose Your Own Adventure. I did the slinky problem. In this lab, we dropped a slinky from the top, from rest, and we wanted to see how the bottom reacted and how the center of mass changed. Now we will discuss the goals, observation, and predictions of this lab. The goal is to be able to predict the future movement of the slinky and the future movement of other objects. We observe the top of the slinky falls and the bottom will not move until the top hits it, and the center of mass moves with an acceleration of -g. In this lab, we will assume that the slinky is constant throughout, meaning the mass is the same in all the little twirls of the slinky, and that the person that dropped it did not give any push, and the only force acting on it is the force of gravity. Newton's second law is crucial in this lab. This slide will explain Newton's second law and how we used it. We know that Newton's second law is F net equals m times a. We also know that acceleration is the final velocity minus the initial velocity. So if we manipulate the equation, we can get that F net times t equals the mass times the velocity of final minus initial velocity. The momentum principle can also be used in this lab for a very similar concept. We know the momentum principle is F equals dp over dt, which can also be said as it equals d times mv over dt. And using this equation, we can say that it equals mass times velocity. Now we will discuss the connections with the fundamental principles in this lab. Some important equations that we used in this lab is Newton's second law, the momentum principle, and Hooke's law. For our glow script code, we started with L not equaling 0, and the drag force was introduced for stabilization at the very beginning. Then the top section of the slinky was released. The mass of each section of the slinky equals the total mass divided by the number of sections, and the model is similar for all choices of length and mass, so we just chose values for L, M, and K. Getting into the actual code, we start with the forces that are pulling down the top section, which is gravity and spring force. Then we move to the forces pulling on the middle section, which is the two spring forces and gravity. And then we move to the forces pulling on the bottom, which is gravity and spring force. Next, we'll loop through the sections for Newton's second law and then update the springs. Here is the model that our glow script code outputted. Going over our results, our model shows that the bottom of the slinky stayed in the same spot until the top passes through or it hit it. Typically, a collision model would show that the bottom should start moving when the top part of the slinky touches it, and the average acceleration of the center of mass is -g. I chose this model because position versus time graphs have a slope of velocity, and that shows what we want to see. And to accomplish this lab, there were some simplifications made to make it easier to tell what was happening, as you can see on this slide. To discuss the possible sources of errors and improvements that we can make in the future based on this lab, some possible sources of error are that there were a lot of tracker points that had to be made to track the slinky's fall, so there could have been human error when creating the points. And as for improvements, we could drop the slinky somewhere where there's no wind or onto a surface that was smooth so that we could analyze the movement once it hits the floor. To wrap this up, we know from the lab that F net stays at 0 the whole time, so when the slinky was dropped, the bottom of the slinky did not move until the top of the slinky hit it, and the bottom of the slinky stays with F net in equilibrium until the top spring force of the section above changes it. We can also conclude that the slinky behaves like a wave. I hope you have a great day.